Good morning. We should start. So, a warm welcome to our presentation regarding using AI accelerators in low-power edge devices. I am Dávid Isztl, and he's my colleague Patrick Caesar. And I think we're ready to start. What you're seeing here is the type of devices that we're focusing on. Our focus are tensor processing units of the size of 5 times less than a cent. They have very little memory and use very little power. They use only quantized 8 bits, and they allow us to run devices with high accuracy for years on a single battery without any human intervention. There are multiple actors in this field. For example, Coral is a device introduced by Google. Their approach is something like having a main tensor processing unit and another package which features an ARM core. The idea here is that they interconnect via USB 2 and they accelerate neural networks with accelerator when needed. This uses little power according to Google. In fact, this is their ultra low power solution. Another player is Maxim. Maxim has produced the latest chip, Max 78002, and their approach is slightly different. Instead of having a tensor processing unit to accelerate neural networks, they have a package which includes an ARM, RX5, and a neural network accelerator. And most importantly, they don't have a USB 2 bus between them. It uses very little power. Now, to have this in numbers, we put together this small table. What is very important here is that we can see the average inference power consumption, which drops from 3 watt from Google to 0.07 watt. At the same time, for the peak inference consumption, which may be hit during inference time, is also reduced from 9 watt to 0.5 watt. When you have such a device in sleep, for example, on a single battery, you move from 62 days to 416 days.
Thank you. So now you get a rough idea in which dimension we are working in space of low power. So we are not talking about the low power of 9 watts. We are talking about the 0.5 watts. Actually, we even want to go further down. So we have a project, an InnoSwiss project with Miromico and SBB. And our main goal is to develop a platform that's using only 150 microwatts over 3 years. And we can drive it with a typical lithium AA battery for this time. So therefore, we developed such a hardware. We have here basically our board. This is the Maxim chip, the accelerator we showed earlier. And this is a LoRaWAN module from Miromico. And around it, it's a baseboard for the development. And because the chip will never reach this 150 microwatts we want to get to, we had to use an additional concept, but that we will tell you later on. So, but why do we want to use that?
So one of the main problems that we decided to tackle is, wouldn't it be amazing to be able to count free parking spots in a huge parking lot for years without any human intervention? And the answer is, you could do that. This is a model that we designed. You can find this at our booth. You could train a neural network that runs on a GPU. You could use 125 watt per inference, and you can detect where the cars are. With our solution, for the same input, yes, you can use only maximum up to 0.5 watt and have the same exact accuracy.
So, thank you. now we talked about a little bit about the story, what device we want to have, we want to use. But now we want to actually go into the topic, how are we doing that? And we focus on 3 points in the next few slides. The first one is the hardware CNN accelerator that we have on the Maxim chip. We are talking a little bit about that. Then afterwards we'll talk about the quantization, and the trigger solution that I mentioned earlier will follow at the end. So I will start with the CNN acceleration part. This is basically a typical neural network or convolutional neural network we are using in such a device. We have the base operation of convolution, batch normalization, and activation function, some pooling. I won't explain everything in detail, but just to show you basically a brief overview of what we are talking about. Now, what is the accelerator doing? On the Maxim chip, we have 64 parallel processors, and each processor includes a pooling unit and a convolution engine, basically in a fused layer structure. This means all the basic operations can be done in one step. So we reduce the power usage because we don't have to speak between steps with memory, and we limit the way the data has to go. Yes. So this is like the typical operation that the accelerator is doing. To reduce the power usage, this is an important point, that you don't have to run many clock cycles for one operation and to use as less memory that you can. In the hardware, it's also, you have 8-bit registers, so we are using only 8-bit integers because it's using much less power than float 32. And that's why we come to the next point, and that's the quantization.
Quantization is what allows all this to happen. Without quantization, we could not run such a high accuracy on such a small device. Quantization is the action of mapping a float 32 into an assigned integer 1 byte range. This allows you to have a 4 times smaller network in size. This is fairly obvious as you move from 4 bytes to 1 single byte per weight. Plus, you achieve 1.5 to 5 times faster inference time, also because the network size is highly reduced. You can observe the benefit of this on existing networks such as MobileNet or ResNet, and you can see that in each case, the inference time is drastically reduced by maintaining the same accuracy. Unfortunately, quantization is lossy. In fact, when we lose bits, it's impossible to maintain the amount of information. You can observe this with your eyes, or you can observe this by trying to fit a curve to a lower bit range. As you can see, we can approximate how such a curve will behave, but it's impossible to maintain all the information that it's available in the original curve. Today we have 3 ways to obtain a quantized network. The first one, which is also an older technique, is called post-training quantization. In fact, here you train normally, as you will do in your everyday. And what you do in a step afterwards is to transform these 4 byte weights into a single byte integer. The cutting edge that we're using today is quantized aware training. Here, we still train with float 32, but we add simulated quantized layer inside the training. And then the third step, or the third way, which is incoming, was announced by TensorFlow a month ago, is actually quantized training. To dig deeper into this post-training quantization, we can observe that we have many ways to do this today. Patrick. Some require data, but all of them allow you to have a size reduction up to 75%. Now, why some require data and some don't? The reason is that many ways were tried to achieve this quantitative network. Some provide better performance, some provide lower performance in terms of accuracy. The big problem with this is that there is always a difference between the quality of the inference from floating point when compared to the quantitative network. The calibration is important because some try to dynamically quantize the weights during inference time, which is very expensive, and some try to actually run some of your test data to evaluate how to move optimally the weights in a quantitative network. When you observe a quant-aware training, we can see that here, during a convolution, we insert emulators. These emulators do nothing else than introduce the error that will be introduced at the end by quantization. These simulators map the weights into 1 byte, 8-bit, and map them back into floating point. This results in a higher accuracy at the end of the training, but it also requires a longer training. To put this in numbers, we can see the training time required for the different ways of achieving a quantitative network. When we train with floating point, we can then quantize it with the post-quantization, and we can see that this requires the time to train the floating point, plus a little time to move this into the quantitative environment. When we train with quant-aware training, so we have simulators included in our network, we have to simulate way longer. When we jump at the last chart here, we can see that in each case, this is the accuracy provided by the floating point training, and this is the accuracy that is maintained when we have emulators, so quantitative aware training. And this is the accuracy that we obtain when we use post-training quantization. It's fairly obvious that the accuracy maintained by the quant-aware training is way higher. Now, to put this in real use cases, we have, for example, an object recognition. This table is kindly provided by TensorFlow. We can observe here that when we do object recognition with the floating point 32, we have an accuracy of 23. When we take this exact network and we do post-training quantization, we drop in accuracy to 0.03. This is unacceptable. When we do quant-aware training, and therefore we use the simulators, we have an accuracy drop of only 2 points for the same network. Of course, latency is in all cases reduced because we have, in fact, smaller weights. Another use case is semantic image segmentation. In this case, we can observe that post-training quantization would be feasible. But we can observe that, for example, in the last example, quant-aware training still produces way better accuracy than post-training quantization. Latencies are, in any case, reduced thanks to smaller weights.
Thank you. So we talked about the quantization and the hardware we are using to accelerate the CNN. Now you saw that the chip is drawing 1 milliwatts in sleep mode, and we have to somehow prevent it from drawing it to get to our 150 microwatts. We showed you one application for the whole project, but we have a whole list of applications that we want to achieve. That's just a little bit of context that you maybe understand a little bit better about what I'm talking about next. A is for audio and V is for video. So we developed a trigger solution that's something like this. That's a development board. We are using triggers to basically wake up the CPU, and then the CPU will use the accelerator. What you see here are 3 PIR sensors with different ranges, so we can 3 meter, 5 meter, 12 meter, depending on what you need. And on the left side, you have 5 microphones that you can trigger on sounds and anything in that way. The target is to have like a modular concept that you just can take your PIR sensor or your microphone you need for your application and plug it in and ship it out. To come back to the whole system as an image, we have basically the IoT platform, as it's developed now, is using the triggers. They are always on. They are at the moment drawing like 200 to 300 microwatts. So we are still improving it. But if an event occurs, say you hear the train coming through a station, then the audio trigger will trigger the CPU. The CPU will then decide what do I have to do, and basically maybe capture an image of the train station because to look what's there, and then it decides to use the CNN accelerator. And because we don't have to run always the accelerator, we can over the 3 years span of time get through this 150 microwatts in average. Okay. Thank you for listening. We are at the end of our presentation. If you want, you can find all of these applied at our booth downstairs in the ground floor, and we are available for questions now. Thank you.